to this computer so that I know where to find it. So, hello. So this is Monday, the 3rd of April, and I have your exams graded. You should take a look at those. You should take a look at those and see what sort of comments I had on things that you may have had some trouble with. I will say, though, that the grades overall were really good. The few people that didn't do real well, it was mostly because they didn't finish, okay? There was a little bit of people not following instructions. For example, I asked you to please not cram all your answers into a single page. And when I say that you have to understand what I mean, not just literally what I say. If you cram all but 3 of the questions onto one page, that's still doing the same thing. So please, with the final exam, do make it a little bit easier to read by not putting it on the page that the questions are on. And so, yeah. But I did want to comment that the grades were really good on the exam. And looking at grades in the class, a lot of y'all are on track to end up with an A in the course. So we have remaining just the final exam. I am going to try to get that out to y'all on Wednesday if I can, and give you roughly a week to get it finished in. And that will be that. We should be able to have things finished right as finals week is really kicking off. So any questions or thoughts on that?
So everything's pass-fail right now. So would you say it would be a smart idea, since you say most of us are on a track to get A's, to go ahead and opt out of that?
Yeah, thank you for asking that, Nick. And that's exactly where I was going with that. Take a look at what your grade is at. If you are on track to get an A and you feel confident in the final exam, I see no, well, even if you're on track for a lower grade, but it would pull up your GPA, if it would benefit you to do so, I would go ahead and request about getting an actual grade for the class. If, on the other hand, you just don't want the stress, some of y'all, it's, I picked out that there are 3 people in the course who could turn in a blank page for the final exam and still have at least an A- in the class. If you're wanting to keep things pass-fail and you don't want to do the final exam, you can figure on the percentage dropping about 10 to 15 points at the most. And, you know, if you're already getting an A or a B and you take it as pass-fail, that removes a lot of stress from you. So do me a favor, send me an email and let me know if you don't intend to take the final exam, okay? And if you do intend to take the final exam, I should have it ready for you all on Wednesday. So any thoughts on that? All right, let me grab something here and get it to where, yeah, that'll show me. All right, so along those lines, the exam 3 has been graded and stuff, and everybody turned something in. I will get a solution key to y'all shortly. I haven't written one out, but I'll write one out probably later on today and post that. But we also have coming up the final exam, and I would like to go ahead and show you what that is going to look like. So give me just a second here, and I will bring up, actually there's probably no good reason to do this on the iPad other than the fact that I think it's kind of fun. So this is my outline that I've got for the final exam. I'm going to put a question on there that has you working a trigonometric equation, something that's not super complicated, but I did feel as though we might ought to have a little bit more of that appear. And then I'll have a problem that has you working out law of sines in the angle side angle case. So that would be something like this, where you're given maybe this side and these two angles. Then by subtraction, you can find out that third angle, and then you can just set up law of sines and solve. Similarly, I might give you something where you get the angle, and a side that's not included. Same sort of thing of use subtraction to figure out the remaining side, or the remaining angle, then you set up the law of sines to get the sides. Something where you've got the ambiguous case to work out, and that is to say that you know the lengths of these two sides and this angle, and there's two different ways that you could put this this shorter side in here, and so you have to work out those two details. We did one like that in class. So something where you've got the law of cosines, and you're given two sides and the included angle, and you have to figure out the remaining sides and angles. So the side case of law of cosines is what it sounds like. You're given the length of the sides and asked to figure out the angles. Once you've got two of the angles figured out, you can do the third one by subtraction. Then I'll have something where you essentially have to use law of sines, law of cosines in order to figure out something about a triangle, one of the angles, one of the sides, something like that. But where it's an application and you only really need to do one solution there. So I'm going to put a problem on that has you doing some sort of vector arithmetic, vector algebra sort of thing. Something where you have to look at directions and magnitudes. And we're going to talk about dot products and angles today, and I'll put one of those on there. Once you see what those are, you're probably going to be pretty well disposed toward working one of those problems. They're not super hard, okay? And then some sort of vector application. We worked one on Friday, and then I made a video of another one and included that on the links for the Friday class. The applications get kind of painful just because the numbers are yucky, you know, but I'll sit down and try to figure out one of those where the numbers are not too awful, okay? But that's what I'm looking at putting on that final exam, and I'm looking at having that ready for all Wednesday and giving you a week to work on stuff. So do folks feel okay with that? Maybe a yes, no, thumbs up, thumbs down. So yay. Okay, cool. All right. So if you're cool with that, what I want us to talk about today is actually taking a look at section 6.7. And 6.7 is again dealing with vectors, but it's adding this new idea in there about the dot product. So let me jump over to that and share that screen with you. And I'll have to do that over again. Sorry if that made you all dizzy. And up, there's the airplay. All right, so we're taking a look here at this section 6.7, and the title on that, as you can see, is dot products. So this thing that we refer to as a dot product is simply multiplying the coordinates, the corresponding coordinates of two vectors, and then adding up the result. Sounds maybe too straightforward to be true, but it's not. So if we're calculating -1, 4 dotted with 6, 3, you take the -1 times the 6, those are both x coordinates, plus the 4 times the 3, and you have -6 plus 12, and your answer is +6. Y'all feel good with that? So, all right. Then what I'm going to ask y'all to do is take just a second here and do this dot product and see what you get. As soon as you've got something, or you come to a point where you don't feel like you can finish it, please go ahead and give me a thumbs up or a yes or no or something. Good. Okay. All right. So going ahead and working this out here, we'll have 3 times the -4 plus 4 times the 3. So it's -12 plus +12, which of course turns out to be 0. So everybody feel good with that? All right. Then let me make this brief note here. I'm going to try to draw a sketch real quick and show you something kind of neat about these. So 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. I tried to space those as evenly as I could manage. But now if we look at the vector 3, 4, it's about like that. Now that's not quite. Let me undo that. It's about like that. And then -4, 3 is about here. And so if I do that, so those two vectors you can see have the same length on them, but the thing that is, if I had this on a super good drawing, you could tell is those two vectors are at a 90-degree angle to each other. So what we find is if u vector dot v vector equals 0, they form a 90-degree angle. So we use the term perpendicular when we're doing geometry, and we use the term orthogonal when we're doing a branch of math called linear algebra. Okay. Oh, looks like Eddie bailed ship on us. Okay. So So if we have two vectors that are perpendicular or orthogonal to each other, their dot product will turn out to be 0. So that might remind you of something, which is that the cosine of 90 degrees, remember how that cropped up in the law of cosines? The cosine of 90 degrees is 0. The place that it showed up in the law of cosines was that if you wrote out your terms for the law of cosines, it had a cosine appearing in it. And if the angle was 90 degrees, then the extra term dropped off and it suddenly turned into the Pythagorean theorem. So that is going to come up here with this thing we've got. So we've got as a consequence of the law of cosines, when you take the dot product, it will be equal to the magnitude of the two vectors and then times the cosine of the angle in between. So this, I want to go ahead and try to show you real quick why this actually is. And for that purpose, I went ahead and got a diagram here where we took our two vectors, maybe this is u here, and maybe this is v here. And then if we connect the two with a triangle, because of the way that vector addition works, you want, when you add this vector to that vector, because you end up at the same place, you want to get a result when you add them on that being v. So if I were to go ahead and tell you that my u vector has u1, u2 as the entries, and my v vector is v1, v2, then of course v minus u should just be the difference there. So v1 minus u1, v2 minus u2, like that, okay? So the thing that we're going to write down here from the law of cosines is going to be that we have this angle here, theta, and then the side opposite it. And writing down the law of cosines would be the magnitude of v minus u squared would be equal to the magnitude of u squared plus the magnitude of v squared minus 2 magnitude u magnitude v cosine of theta. Okay? So if you remember, when we take these magnitudes, that's going to be a square root of the sum of the squares of the entries. So the most complicated one will be right here with the left-hand side. But when we square that magnitude, it'll take care of the square root, and we'll end up with v1 minus u1 squared plus v2 minus u2 squared. And then over here on the right-hand side, we'll have u1 squared, u2 squared for the first one, v1 squared, v2 squared for the second one. And I'm not going to mess with the rest of it, okay? But here, when we square those out, minus 2 u1 v1 plus u1 squared plus v2 squared minus 2 u2 v2 plus v2 squared, and it's supposed to be equal to that stuff up there. And if you notice, there's a v1 squared on both sides, and there is a u1 squared on both sides, and a v2 squared and a u2 squared. And we actually cancel out all of our cancel out all of our squares. And if we factor out that -2, and cancel it on both sides, we actually have u vector dot v vector appearing on the left, and magnitude u vector, magnitude v vector, cosine of theta. So it turns out this weird little rule that we've got here is just the law of cosines in a really weird disguise. So, folks feel okay with that? Yes, no, maybe? I see one yes. Okay, all right, cool, thank you. All right, so moving on there, we're gonna go ahead and find the angle formed by, and I just made up like a couple of random vectors here. And so to find the angle, we're gonna remember this u dot v. So we'll call this one u, we'll call this one v, is gonna be magnitude u, magnitude v, cosine theta. So we can calculate u dot v pretty easily. We'll take -9 times -1, and then we'll take 10 times 10, and so we'll end up with 109 for the dot product. Then the magnitude of u is this square root of 9 squared plus 10 squared. So that'd be the square root of 181. I don't think that simplifies. Magnitude of v is going to be the square root of 1 squared plus 10 squared. So the square root of 101. Again, I don't think that simplifies. And so we're going to fill in everything we know. 109 equals square root of 181, square root of 101, cosine of theta. So that says that the cosine of theta is going to be 109 over those two square roots. And I am not going to be able to do those in my head. And I don't have a calculator I can bring up on the screen for you to see. But I've got one beside me here. And so I've got to hit the right buttons. 101 and 181. And so I'm getting about 0.806, all right? And so for my theta, I'm going to get the inverse cosine of whatever it was that I just got there. And so second cosine, second answer, I'm getting about 36.277 degrees. Might as well on that just call it 36 degrees, right? So that's kind of rapid fire, but y'all feel okay with the idea of that? Okay. All right. Oh, looks like Ben joined us too. So thank you. So the thing that you might make as an observation of this, if you are a very good artist, is you might say to yourself, well, heck, I am not going to do that. I'm going to just all the time draw my vector here. Pretend that's -110. And my vector here, let's see, I lost my place, -9. Sorry, negative 110 would be like that, and negative 910 would be like that. And then if you draw a really good picture, you can put a protractor in there and figure that out to a pretty accurate degree. In fact, when I was in high school, when I took trigonometry, one of the students was the teacher's son, and he absolutely refused to learn any trigonometry, and that's exactly what he did all the time. The thing is, this allows us to do things in 3 dimensions. It doesn't have to be in just 2 dimensions. So if you have 2 vectors that are 3-dimensional, and we'll get an example of that here in a minute, you can figure out the angle with things that you cannot physically draw. So, well, you can draw them, but yeah, okay. All right. So this example here, we're going to have a triangle with these 3 vertices. I think we actually had the same triangle as an example the other day. And so all right. So negative 1, 4 would be roughly here. 0, 0 is the origin. And 1, 2, 3, 4, 5, 6, 3 would be here. And so that's the triangle we're looking at. So we need to figure out what some of the angles are. Let's start with this one here. I'm going to call this O, call this P, call this Q, just to have things to call them. And so I am going to look first of all at OP vector, because that's pretty easy to figure out. And I'm going to figure out OQ vector. So that's also pretty easy to figure out. And now I want to figure out what the angle is that's formed by them. To do that, and I'll write it as cosine of theta, I'm going to take the dot product on top, OP dot OQ, and divide by the magnitude of OP and the magnitude of OQ. So the dot product we should be able to do pretty easily. Negative 6 plus 12. So we have a 6 on top. Then the magnitude here of OP is going to be the square root of 1 squared and 4 squared. So square root of 17. And then the magnitude of OQ is going to be the square root of 36 squared and 3 squared. So that's, I said the wrong thing. And the square root of 6 squared and 3 squared, which will end up being 45 here. So our number that we get turns out to be about 0.217. And so that angle I'm going to get as an inverse cosine of that 0.217. And again, I don't bother getting these past like the nearest degree. That's about 77 degrees. Good enough, okay? And then we're going to figure out another one. So we can do either P or Q. Once we know one of them, we know the other one. I think maybe I'm going to try to do stuff with P, right? So that means I will need to know what's PQ and what's PO. Well, PO is just going to be the opposite of OP. So 1, negative 4. PQ, we have to think we're going from negative 1, 4 to 6, 3. So the change that we get in our x's we have to increase by 7. And then changing our y's, we have to go down by 1. So we get that 7, -1. So when we say the cosine of p, then up top, we're going to have the dot product. So PQ dot PO. And I realize that my handwriting became a problem there. So the dot product then divided by the magnitude of PQ and the magnitude of PO. So the dot product is going to be 7 plus 4. Okay, so 11. And then those magnitudes, we're going to have a magnitude on the PQ that is the square root of 50, because 7 squared and 1 squared. And on PO, we're going to have a magnitude of 17, because it'll be the same as the one before. And so if we punch that up in the calculator, I'm getting about 0.377. Okay. So the P is going to be the inverse cosine of whatever that was. Now I'm getting about 68 degrees. Okay. So then the thing that's left is going to be your Q, and you'll just take 180 minus 68, and minus 77. And I'm getting about 35 degrees. And just roughly eyeballing what those angles are that we have in the sketch, those seem like they're in the right ballpark. So how do folks feel about that? Yay, yay, okay. Looks like everybody feels pretty good. Awesome. So I had left a blank space in there. So we're going to take a look at another one here. And this is one that kind of tends to bedevil me. I remember when I took a high school physics class way back when, it seemed like we were always doing this kind of problem here. And so we've got the vector that is the weight pushing straight downward. And what we're wanting to see is how much of that weight is pushing parallel to the plane and how much of it is pushing perpendicular to the plane. Okay. So with regard to that, we're going to look at that 8 degrees for the plane, and we'll think about getting a vector that points in that same direction. I'm going to refer to that as U, and it will just be cosine 8 degrees, sine 8 degrees. If you want to punch up and get numbers in your calculator, you certainly can, but I feel like that's kind of messy. The whole thing is going to be messy, but I feel like that's messier. Okay. So then the vector, which is the perpendicular here. So remember, that's this direction here, right? If we think about this on some axes here and have 8 degrees here, a really logical way to look at this is to just rotate 90 degrees and then have negative 82 degrees there. So we'll have the cosine of negative 82 degrees and the sine of negative 82 degrees. And so, all right. So then we're wanting to figure out we're wanting to figure out what to do about these to get the part that is pointing the directions that we want. And in order to see that, I'm going to look at something to the side here real quick and point this out to you. If I have the vector 1, 0, and I have the vector 0, 1, and I have some other vector, maybe say this is the vector 3, 2. Note that when I take the dot product with that unit vector, it will tell me how much is going in that same direction. So if I take 3, 2, and I dot it with 1, 0, I just get 3. And if I dotted it instead with 0, 1, I would just get 2. So if we've got our weight vector here, which is pointing downward, so it has no x component, and it has a y component that is negative 25, we can just take u dotted with w. So cosine 8 degrees, sine 8 degrees, dotted with, and did not leave myself room, 0, negative 25. And that's going to be negative 25 sine of 8 degrees. So I am again using the calculator here to get about negative 3.479, and that'll be in pounds. And when I do the V dotted with the W, so that I have the cosine of negative 82 degrees, sine of negative 82 degrees, I'm dotting that with 0, negative 25, I end up with negative 25 sine of negative 82 degrees, which is about 24.757 pounds. Okay, so what does that tell us? That tells us that almost all of the force that we're talking about is going to be the part that is going down perpendicular to the ramp here, and very little of it is going in this direction. Notice that we did get a negative number here for the part that's parallel to the ramp, and that does mean that it's tending to make it slide down the ramp as opposed to, you know, somehow having the weight push it up the ramp. So if you were in an actual physics class, then there might be questions about the amount of friction on the ramp and deciding whether or not the toolbox would slide down the ramp. I will have to admit to y'all that that is outside of my actual realm of expertise. So anyway, how do y'all feel? Good? Okay. All right. Yay. Thank you. So I left a little bit of extra room there, but here is another example. This is a more mathy kind of example, but it's introducing this idea of 3 dimensions here. Okay. And so we're going to use the dot product and find an angle between the diagonals of a cube. And what I mean by the diagonals of the cube are actually the diagonals of the faces of the cube. we'll have another problem here in a second where we'll mean something slightly different by diagonals. But in order to figure this out, we're going to think about, maybe I should use black on that instead. We're going to put axes on here so that the origin is at one corner of the cube and the other corners we can figure out using vectors. So in particular, I'm going to think about this is the x-axis down here, this is the y-axis, and this is the z-axis. And I am going to make the length of these edges all be 1, so that this point here is going to be the point 1, 0, 0. This point over here is going to be the point 0, 1, 0. And this point right here will be 0, 0, 1. Y'all okay so far? Okay, yay. All right, so that means that this corner here lines up with the 0 in the x part, 1 on the y part, and 1 on the z part. And this corner here lines up with the 1 on the x part, the 1 on, the 0 on the y part, and the 1 on the z part. This one here lines up with 1, 1, 0. And then finally, this one here lines up with 1, 1, 1. Okay? So we're going to go along with this. And I'm going to put, I think blue will show up fairly well here. We're going to put this diagonal here and this diagonal here in as vectors. Okay. And then we're going to figure out what the angle is that's formed by them. So if we're going to put those in, we'll have to give these names. I'll call this one P, and I'll call this one Q, and I'll call this one R. Okay. So I'm going to have to figure out what the PQ vector is and what the PR vector is. Okay. So think about these in terms of what changes. So if you are going from the point 1, 1, 1 to the point 0, 0, 1, the x coordinate had to go down by 1. Oh, I was starting the wrong one. Sorry, folks. We're going from P to R, so that would be the PR vector. So the x went down by 1, and then the y coordinate also went down by 1, but the z coordinate stayed the same. Then for the PQ vector here, the x coordinate, let's see, the x coordinate stays the same. The y coordinate goes down by 1, and the z coordinate goes down by 1. So if we want to figure out what our angle P is here, we have to take the dot product on top, PQ dot PR, and then we have to take the magnitudes of both of them on the bottom. So the dot product on top, notice that we've got them lined up here. 0 times -1 is 0. -1 times -1 is 1. And -1 times 0 is 0. So of the things that we're adding up, only one thing is non-zero, and it ends up with a 1. And then we have to figure out what the magnitudes of these things are. But of course, the magnitude is a square root of the sum of the squares. So 0 squared plus 1 squared plus 1 squared. So we end up with a square root of 2. But that happens on both of them. Square root of 2, square root of 2. So we end up with 1/2. Since the cosine of p is 1/2, when we figure out what the inverse cosine is, it just so happens it's a nice angle, one of our special angles, and the p is going to be equal to 60 degrees. The reason that that is nice, I think I've got a picture on the next slide, but the reason that that is nice is that means that if we connect these diagonals like that, we get an equilateral triangle. And so looking here on the next slide, this means that if you take a cube and you draw a diagonal across faces in such a way that you have things meeting in 3 points here, you will end up making a tetrahedron that's inside of that cube. That makes for just kind of a really neat image of a tetrahedron then inside of a cube. So I think it's neat anyhow. So stepping back here, do y'all feel okay with the calculations that we did there? Okay. All right. Yay. Thank you. All right, then we've got one more to do. That's an application. And this is something that's more of a chemistry application. And to be honest, lots of chemistry applications are just beyond what I can actually get figured out. But when we talk about iron atoms forming a crystal lattice, the way that they form these is by having one atom here, like at the center of a cube, and then more atoms landing out at each of the corners. And because of the way those bonds are, it ends up being a very strong lattice. So we're going to take a look at this, and we're going to think about it being in 3 dimensions. And much like before, we're going to think about the origin here, the 0, 0, 0, being this one dot that's right there in the center. That's going to be 0, 0, 0. And then another one will be 1, 1, 1. But then this one over here, we're going to have one of the coordinates be negative. So that could be either the x or the y, but it looks like the z should be the same. Okay. So if we're wanting to find this angle that's being formed there, we'll think about this as O, and this is P, and this is Q. So the OP vector, nicely enough, is going to be 1, 1, 1. The OQ vector is going to be 1, -1, 1. And we ought to be able to see that the magnitudes, because that's going to show up in a minute, are going to be equal, and they're going to be the square root of 3, right? But if we want to do the cosine of the angle O, I hate the way that looks. I'm going to refer to it as the angle theta, okay? We can say OP dot OQ, P, and then divided by the magnitude of OP and the magnitude of OQ. So taking that dot product, we're going to see 1 minus 1 plus 1. And on the bottom, square root of 3, square root of 3. So we end up with 1 over the square root of 3 as our cosine. So the angle that we want is going to be the inverse cosine of 1 over the square root of 3. Now that's not a special angle. It feels like it ought to be because, you know, tangent being equal to 1 over the square root of 3, that is a special angle. But if we do this, we end up getting 54.7 degrees. Again, with chemistry, I'm not real good with it, so I'm not super confident about how much detail you need on that. But how do y'all feel about that particular one? Good, good. Okay, all right, cool. So I had left myself some extra space there because I thought that one might be a little bit rougher than it actually was, but it kind of looks like we've got everything figured out. How do y'all feel? Okay. All right. So I'm going to go ahead and hit the stop button here for the recording.